Okay, so today we'll be looking at number 8 on homework 2. So in number 8, it shows a standing wave oscillating at a frequency of f sub 0, and there's a two-part question. So the first part is asking how many antinodes will the standing wave oscillation have if you double your frequency? And the second part, part B, is asking if the tension of the string is increased by a factor of 4, what's the frequency in terms of your original frequency needed to stay oscillating as a standing wave with 4 antinodes? So we'll jump into part A right now. So I've drawn out your original standing wave oscillation with f sub 0 as your frequency. And now I've drawn out with the frequency doubled. So since these lengths are both the same, the distance at which the waves are traveling, you're not changing that. So in order to increase the frequency in the same distance, you're going to have your wavelength. So this has twice as many antinodes as this one because you have a smaller wavelength. There's more waves per length. So when your frequency is doubled, your wavelength is halved. And as a result, having your wavelength will double the amount of antinodes you have. So your original frequency has a total of 4 antinodes. So if your number of antinodes is doubled when your wavelength is halved, you're going to have 8 antinodes now. So your number of antinodes will increase from 4 to 8. And that's the answer to for part A. So moving on to part B. So now we got to figure out what's going to happen to the frequency if you increase the tension on your string by a factor of 4. So let's write out our tension equation right now. So we have V equals the square root of T over mu. And our new tension, this is our starting tension. If we quadruple our tension, the new equation is going to be V1 is equal to the square root of T1 over mu. And T1 is equal to 4T over mu. So when we use a square root, when we solve this equation, we get this is equal to 2 of our original V. So now we're going to try and see what happens to our frequency. So let's find our equations that relate our V and our F. So we have V equals your wavelength times your frequency. And that would mean that to start, our V would equal our original wavelength, lambda sub 0, and times f sub 0. And our end equation, V1, is going to equal your wavelength times your frequency again. But our wavelength is going to be the same. We're only increasing the tension. So we can say lambda 1 is equal to lambda sub 0. And we can also say that our V1 is equal to 2V, as proved up above. So now we're going to plug in, just kind of plug and chug we have lambda 1, F1 is equal to 2 lambda 0, F0. And since we said earlier that lambda 1 is equal to lambda sub 0, we have lambda sub 0 times F1 is equal to 2 lambda sub 0 times F0. And we get rid of some of these factors, and we get our new frequency, F1 is equal to twice our old frequency. So, if you quadruple your tension, if you multiply your tension by a factor of 4 and you increase the tension in the string, you will get a frequency that is twice as high.